Imagine a technology so advanced that it completely shatters the laws of physics as we know them. A spacecraft capable of traveling at 1 light-year per second. Light itself, the fastest thing in the universe, needs an entire year to cross that distance. But with this impossible machine, you would cover it every single second. At that speed, the universe stops being distant. Stars are no longer unreachable. Galaxies are no longer abstract ideas. Space itself becomes a road. Our journey begins here, on Earth, a small blue world orbiting an ordinary star, tucked away in an unremarkable corner of the Milky Way. From this quiet starting point, we will leave everything familiar behind. In moments, planets will vanish. In seconds, stars will surround us. And in time, measured not by clocks but by scale, we will move from our cosmic neighborhood to the very edge of everything humanity has ever observed. This is not a journey bound by reality. It is a thought experiment, one that allows us to grasp the true size of the universe. In Part 1, we leave home. We race past the solar system, cross interstellar space, and explore nearby stars, alien worlds, and colossal suns that live fast and die violently. In Part 2, we go further. Beyond individual stars, beyond galaxies, beyond clusters of galaxies, toward the largest structures ever discovered, and finally, to the edge of the observable universe itself. So take a breath, because once we begin, there is no slowing down. The journey begins on Earth, a small, fragile world suspended in darkness, orbiting an ordinary yellow star. From the surface, the universe feels distant, stars reduced to pinpoints of light. But the moment our spacecraft ignites, that illusion disappears. In the first second, we surge past the inner planets. Mercury and Venus vanish without ceremony. Earth becomes a pale dot behind us. Mars flashes by, followed by the gas giant Jupiter, its endless storms frozen into a shrinking sphere of color. Another second passes. Saturn's rings collapse into a thin line. Uranus and Neptune fade into the black. We tear through the Kuiper Belt, a vast halo of frozen debris, ancient remnants left behind from the birth of the solar system. Almost instantly, we reach the heliopause, the invisible boundary where the sun's solar wind finally surrenders to interstellar space. Here, the influence of our star ends. Beyond this point, there is no shelter, no warmth, only the deep, silent ocean between stars. After 4 seconds, a new sun rises ahead of us, Alpha Centauri. The closest star system to Earth, located 4.37 light-years away, appears not as one star, but 3. Alpha Centauri A and B orbit each other in a delicate gravitational dance, while the faint red dwarf Proxima Centauri lingers nearby. Around Proxima, at least one planet circles within the habitable zone, a world that could, in theory, support liquid water. This system has become humanity's first true interstellar destination, a reminder that even in the cosmic wilderness, neighbors exist. At 8 seconds, we arrive at Sirius, the brightest star in Earth's night sky. What looks like a single beacon from afar is actually a binary system. Sirius A burns hot and white, while Sirius B, its companion, is a white dwarf, an object so dense that a teaspoon of its matter would outweigh a mountain. These stars mark the transition from familiarity to strangeness. At 40 seconds, we encounter 55 Cancri E, an alien world beyond anything in our solar system. It orbits so close to its star that its surface temperatures exceed 1400 degrees Celsius. Beneath its crust, immense pressures may compress carbon into vast layers of diamond. A planet shaped by extremes where geology itself behaves differently. As the seconds stretch into minutes, stars grow larger, more violent. At 14 minutes, we pass near Rigel, a blue supergiant burning over 100,000 times brighter than our Sun. Stars like this live fast and die young. Their short lives end in catastrophic supernovae, explosions powerful enough to forge the heavy elements that later become planets and life. We are no longer just traveling through space. We are traveling through the life cycles of stars, and this is only the beginning. In Part 1, we left home. We crossed the solar system, touched neighboring stars, and witnessed worlds of fire and suns that burn their lives away in brilliant violence. But individual stars, no matter how massive, are only the beginning. Now we move outward. As minutes become hours, the stars around us begin to blur together. Their distances stretch beyond intuition. What once felt like a crowded neighborhood reveals itself as a vast, mostly empty ocean. Then, slowly, structure emerges. After 2 hours, towering shapes rise from the darkness, the pillars of creation within the Eagle Nebula. These colossal columns of gas and dust span several light years, sheltering newborn stars within their shadows. Radiation from nearby massive stars is already tearing them apart. Creation and destruction occur side by side, sculpting the future of the galaxy. At 5 hours, we pass near VY Canis Majoris, a red hypergiant nearing the end of its life. If placed at the center of our solar system, it would engulf Jupiter. It sheds enormous amounts of mass, forming glowing shells that drift away into space, a slow-motion prelude to a coming explosion. Within 1 day, we reach the edge of the Milky Way. From this vantage point, our galaxy reveals itself as a vast spiral of stars, dust, and dark matter, home to hundreds of billions of suns, yet only one among countless others. After 29 days, another giant fills our view, the Andromeda Galaxy. Bound to the Milky Way by gravity, it is rushing toward us. In 4 billion years, the two will collide, merging into a single, immense galaxy. Galactic time moves slowly, but its outcomes are inevitable. At 115 days, we leave the local group, a small collection of galaxies drifting together through space. Beyond it lies a realm where galaxies gather into enormous clusters. After 3 years, we cross the Virgo supercluster, containing thousands of galaxies arranged along invisible filaments. And by 16 years, we exit Laniakea, the vast gravitational basin that includes our own galaxy and everything near it. A century into the journey, we approach TON 618. This is not merely a black hole, it is a cosmic titan. With a mass of 66 billion suns, it shines as a quasar, powered by matter falling toward a point where space and time lose meaning. After 320 years, we pass the Great Wall, one of the largest known structures in the universe, so immense it spans a significant fraction of the observable cosmos itself. Finally, after 1,000 years, we reach the edge. Not a wall, not an end, but a horizon. This boundary marks the limit of time, not space, the farthest distance light has been able to travel since the universe began 13.8 billion years ago. Beyond it, the universe may continue endlessly, but its light has not yet reached us. Standing here, at the edge of everything humanity has ever seen, one truth becomes clear. The universe is unimaginably vast, and yet the desire to explore it is even greater. As we leave familiar stars behind, something extraordinary becomes clear. Planets are everywhere. For most of human history, we believed worlds like Earth might be rare, perhaps unique. But as our journey continues, star after star reveals its own system of planets, each shaped by forces far more extreme than anything in our solar system. At 40 seconds into our flight, we encounter one of the most infamous of these worlds, 55 Cancri e. This planet orbits its star so closely that a year lasts less than 18 hours. Its surface temperature exceeds 1,400 degrees Celsius, hot enough to melt rock. Lava oceans may glow across its surface, while violent volcanic eruptions reshape the planet continuously. Deep beneath its crust, immense pressure may compress carbon into vast crystalline layers. Not a poetic metaphor, but literal diamond formed on a planetary scale. This is not a failed Earth. It is a reminder that planets do not follow a single blueprint. Minutes later, we arrive at Kepler 22b, one of the first planets discovered in what astronomers call the habitable zone, the narrow region around a star where liquid water could exist. Yet even here, certainty vanishes. Kepler 22b is larger than Earth. It may be a super-Earth with continents and oceans, or a global water world with no land at all. Its atmosphere could be thick with clouds, hiding its surface entirely. From afar, it looks promising. Up close, it remains a mystery. And it is not alone. Some exoplanets orbit two stars, rising and setting beneath twin suns. Others follow wildly elongated paths, swinging from freezing darkness to blistering heat. There are worlds where it rains molten iron, worlds with winds faster than sound, worlds torn apart by tidal forces stretched into glowing ribbons of gas. These planets challenge every assumption we once held about habitability. Life, if it exists elsewhere, may not resemble anything we know. As our speed carries us deeper into the galaxy, the scale becomes overwhelming. For every star we pass, planets follow. Billions upon billions of worlds scattered across the Milky Way alone. Statistically, Earth cannot be special because it is rare. It is special because we are here. Exoplanets are not destinations for us, not yet. They are mirrors. Each one reflects a different outcome of physics, chemistry, and time. Together, they reveal a universe far more creative than we ever imagined. And as strange as these worlds may be, they are still shaped by stars. To understand planets, we must understand the lives and deaths of the suns that give them birth. Every planet, no matter how strange, lives in the shadow of a star. Stars are not eternal. They are born, they burn, and they die. and among them exist giants so vast and powerful that they shape entire regions of the galaxy. As we move deeper into space, ordinary stars like our Sun begin to feel small. At 14 minutes, an overwhelming blue light fills our view. We are approaching Rigel, a blue supergiant located hundreds of light years from Earth. Rigel burns more than 100,000 times brighter than the Sun, consuming its nuclear fuel at a terrifying rate. Its surface temperature exceeds 11,000 degrees Celsius, flooding space with intense ultraviolet radiation. Stars like Rigel are cosmic engines. They live fast, shine violently, and die young. But even Rigel is not the largest. Hours later, we encounter VY Canis Majoris, a red hypergiant nearing the end of its life. If placed at the center of our solar system, its outer layers would extend beyond the orbit of Jupiter. The star is unstable, bloated, and shedding vast amounts of material into space. Gigantic arcs and clouds of glowing gas surround it, matter that will one day become part of new stars and planets. These giants exist in a delicate balance. Gravity pulls inward. Nuclear fusion pushes outward. When that balance breaks, the consequences are catastrophic. Massive stars end their lives in supernova explosions, events so powerful they can briefly outshine entire galaxies. In those final moments, temperatures and pressures become extreme enough to forge the universe's heaviest elements: iron, gold, uranium. Without these explosions, rocky planets could not exist. Neither could life. In death, stars become creators. Some collapse into neutron stars, objects so dense that atoms themselves are crushed. Others form black holes, warping space and time around them. These remnants are not cosmic failures. They are the foundations upon which future systems are built. As we pass through regions shaped by ancient supernovae, it becomes clear that the universe is not static. It is recycling itself on unimaginable scales. Stars are born from clouds of gas, live brilliant lives, die in fire, and seed the galaxy with the materials for the next generation. Every atom in your body was forged inside a star. And as we continue outward, we are no longer just observers. We are witnesses to the engine that makes the universe possible. As we leave dying stars behind, we move toward their beginning. Between the stars lies not emptiness, but vast clouds of gas and dust, nebulae stretching across dozens, sometimes hundreds of light years. These are the raw materials of creation, shaped by gravity, radiation, and time. After 2 hours at our impossible speed, towering forms emerge from the darkness. We have arrived at the Eagle Nebula, home to the pillars of creation. These colossal columns of cold gas and dust rise like cosmic mountains, each one several light years tall. Inside them, gravity is slowly pulling matter together, forming protostars, stellar embryos hidden from view. Infrared light reveals what visible light cannot: newborn suns igniting deep within the shadows. Yet creation here is fragile. Nearby, massive stars flood the region with intense radiation, carving away at the pillars' surfaces. Stellar winds and shock waves from ancient supernovae erode them grain by grain. The same forces that give birth to stars will one day destroy these structures entirely. Creation and destruction are inseparable. Across the galaxy, nebulae take many forms. Some glow brilliantly as energized gas emits light. Others appear as dark silhouettes, blocking the stars behind them. In some regions, gravity dominates, collapsing clouds inward. In others, radiation tears them apart before stars can fully form. The balance is delicate. When enough mass gathers, nuclear fusion ignites. A star is born. Around it, leftover material flattens into a rotating disk. Within that disk, dust grains collide, clump, and grow, forming the seeds of planets. This process has repeated for billions of years. Our sun was born in a nebula like this one. The atoms in your body once drifted through clouds of interstellar dust long before Earth existed. We are not separate from these regions. We are their outcome. But nebulae are not permanent. On cosmic time scales, they are fleeting, brief moments between chaos and order. The pillars of creation themselves are already fading. In a few million years, they will vanish, leaving only stars behind. What remains is light, and the endless cycle continues. Stars are born, they shine, they die, and from their remnants the universe begins again. From within a nebula, a star feels immense. From outside, it is barely visible. As we continue outward, individual stars merge into glowing rivers of light. The Milky Way, once our entire universe, now reveals itself as a single structure, vast but finite. Within one day, we reach the outer edge of our galaxy. From here, the Milky Way stretches across space as a luminous spiral, nearly 100,000 light-years wide. Its arms are lined with star-forming regions, supernova remnants, and dark lanes of dust. At its core lies a supermassive black hole, quietly anchoring the galaxy with 4 million times the mass of the Sun. The galaxy rotates slowly, completing a single turn every few 100 million years. On that timescale, civilizations rise and fall unnoticed. As we drift farther, other galaxies appear. After 29 days, a massive shape fills our view, the Andromeda Galaxy. Larger than the Milky Way, Andromeda contains over 1 trillion stars. Gravity binds our two galaxies together, drawing them closer at over 100 kilometers per second. In 4 billion years, they will collide, not in violent destruction, but in a slow gravitational dance that will reshape both into a single, enormous galaxy. Galaxies come in many forms. Some are elegant spirals like our own. Others are elliptical, ancient, quiet systems where star formation has nearly ended. Some are irregular, torn apart by past encounters, their stars scattered like cosmic debris. Despite their size, galaxies are mostly empty. The distances between stars are immense. Entire solar systems pass by each other without ever coming close. Yet galaxies are not isolated. After 115 days, we exit the local group, a modest collection of more than 50 galaxies bound together by gravity. Beyond it lies a deeper order. Galaxies assemble into clusters, and clusters arrange themselves along vast filaments, threads of matter stretching across hundreds of millions of light-years. Between these filaments lie enormous voids, regions where almost nothing exists. This is the large-scale structure of the universe, a cosmic web woven from gravity and dark matter, shaping the distribution of everything we can see. And as we follow these threads outward, it becomes clear: the universe is not random. It has structure, it has history, and it is far larger than any single galaxy could ever suggest. As galaxies fall behind us, even they begin to feel small. What once appeared as isolated island universes now reveal deeper connections. Gravity, operating patiently over billions of years, has drawn galaxies together into structures of staggering size. After 3 years of travel, we enter the Virgo supercluster. Thousands of galaxies reside here, bound loosely by gravity, drifting together through the expanding universe. From within, it feels immense. From afar, it is only one region among many. But Virgo is not the full picture. As we continue outward, invisible currents begin to guide our path. Galaxies are no longer scattered randomly. They trace enormous filaments, vast bridges of matter stretching across hundreds of millions of light-years. These filaments intersect at dense nodes where clusters form, while between them lie cosmic voids, regions so empty they challenge the meaning of nothingness. This is the cosmic web. By 16 years, we leave Laniakea, our home supercluster, a gravitational basin spanning more than 500 million light-years. Everything within it, including the Milky Way, is slowly flowing toward a common center, drawn by mass we cannot fully see. Dark matter dominates here. It does not shine. It does not emit light. Yet it outweighs ordinary matter by more than 5 to 1, shaping the universe's large-scale structure like an invisible skeleton. Without it, galaxies would never have formed. Without it, the universe would be nearly empty. As centuries pass, the scale becomes almost impossible to comprehend. After 320 years, we pass along one of the largest known features in the observable universe, the Great Wall. This colossal structure spans billions of light-years, containing countless galaxies arranged in sheets and filaments. It is not a wall in any physical sense, but a reminder that the universe organizes itself on scales far beyond human intuition. Here, even superclusters are merely components. The universe now appears less like scattered objects and more like a single, evolving system, expanding, cooling, and slowly transforming since its birth nearly 14 billion years ago. And yet, for all this structure, there is a limit, a horizon we are approaching. Beyond it, gravity has not yet had time to sculpt matter into form. Beyond it, light itself has not reached us. The largest patterns fade, and ahead lies the final boundary. After centuries of travel at an impossible speed, the universe begins to thin. Galaxies grow faint. Filaments dissolve into darkness. The great structures that once dominated our view slowly fall away. Ahead of us lies not an object, but a boundary. After 1,000 years, we reach the edge of the observable universe. This is not a wall of matter. There is nothing here to collide with. Instead, this horizon marks the farthest distance light has been able to travel since the universe began, 13.8 billion years ago. Beyond this point, the universe may continue endlessly, but its light has not yet had time to reach us. Space does not end here. Time does. Every galaxy we have seen, every star that has ever shone, exists within this cosmic bubble of visibility. Beyond it lies a realm forever hidden, at least for now. Standing at this boundary, the universe feels quiet, not empty, but unfinished. The light that reaches us from the edge is ancient, stretched thin by cosmic expansion, fading into the microwave glow that fills all of space. It is the afterimage of creation itself, a relic of a time when the universe was young, hot, and dense. Here, familiar concepts lose meaning. Distance no longer behaves as expected. Space expands faster than light itself, carrying regions of the universe beyond our reach forever. No amount of speed, no matter how extreme, could cross that barrier. Yet this horizon is not permanent. As time moves forward, more of the universe slowly becomes visible. New galaxies emerge from darkness as their light finally arrives. The boundary retreats, revealing fresh mysteries while concealing others. The universe is not static. It is unfolding. And within it, we are not spectators. We are participants made of star-forged atoms, capable of asking questions the universe itself does not answer easily. Our technology may be small, our lifespans brief, but our curiosity is limitless. This journey, impossible as it may be, reflects something deeply human: the need to understand where we are, how we came to be, and what lies beyond the horizon. The universe does not owe us answers, but we will keep searching. Because every horizon reached becomes the beginning of another. And this is not the end. It is the start of everything still to come. We began this journey on a small blue planet, orbiting an ordinary star, in a galaxy that once felt infinite until we dared to imagine moving faster than light itself. In moments, we left our home behind. In seconds, we crossed the space between stars. And in time measured not by clocks, but by scale, we watched the universe unfold, planet by planet, star by star, galaxy by galaxy. We saw worlds of fire and ice, stars born in glowing nebulae, giants that lived fast and died in explosions powerful enough to create the elements of life. We watched galaxies collide, superclusters emerge, and the cosmic web stretch across billions of light years. We followed gravity's invisible hand until even the largest structures faded into darkness. And finally, we reached the edge. Not an end of space, but the edge of time. The boundary of the observable universe marks the limit of what light has had time to show us. Beyond it, the universe continues, but for now, it remains unseen. Standing here, something becomes clear. The universe is not centered on us. It does not exist for our convenience. And yet, somehow, it gave rise to beings capable of understanding it. Every atom in your body was forged in ancient stars. Every breath is borrowed from cosmic history. We are not visitors in the universe. We are a part of it. This journey was never about speed. It was about perspective. Because when you see how vast the universe truly is, you also see how extraordinary it is that we can ask questions at all. The universe does not promise answers, but it invites curiosity. And as long as we continue to explore, to imagine, to wonder, to reach beyond the horizon, this journey will never truly end. Because the greatest distance we have ever crossed is not measured in light years, but in understanding.